Good morning all. In continuation to our discussion on power law transformation, today we will discuss the case when gamma is less than 1. As discussed earlier, for power law transformation, the mathematical equation of power law transformation, it is S equals to C R to the power gamma, where R is my input intensity level, S is my output intensity level, C and gamma are my constant. The algorithm for power law transformation, it is written over here. First, we have to consider the unnormalized input intensity range. Then we have to convert this unnormalized input intensity range R into normalized input intensity range Rn. Next, on this normalized input intensity range Rn, we will perform the power law transformation and we will obtain the normalized output intensity range Sn. And finally, the normalized output intensity range Sn, we will convert it into unnormalized output intensity range S. So in order to understand the power law transformation for gamma less than 1, let us take the example of an 8-bit digital input image. So for an 8-bit digital input image, n is equals to 8. If n equals to 8, the number of gray label L is equals to 2 to the power 8, that is equals to 256 number of gray labels. Their representation in digital image, it start with the minimum gray label 0 to the maximum gray label 255. So for an 8-bit digital input image, the unnormalized input intensity range R, it varies from 0 to 255. Or in other words, for an 8-bit digital input image, the gray label intensity value will vary from 0 to 255. So for an 8-bit digital input image, we have obtained the range of unnormalized input intensity range, that is R, which varies from 0 to 255. And we want our output and we want our unnormalized output intensity range S will also vary from 0 to 255. Next, we will convert this unnormalized input intensity range R into normalized input intensity range Rn, and for the same we will perform the simple mathematical operation, that is Rn, it is equals to R divided by 255. So for normalization, each unnormalized input intensity value will be divided by its maximum intensity value, that is 255. So now we will determine the range of Rn. For R, the minimum value, it is 0. So now we will normalize this unnormalized input intensity value 0 with respect to its maximum intensity value 255. That is 0 divided by 255, it is equals to 0. Next, the maximum value of R, it is 255. Next, we will normalize this intensity value 255 with respect to its maximum intensity value 255. That is 255 divided by 255, it is equals to 1. So Rn will vary from 0 to 1, and we want our normalized output intensity range Sn will also vary from 0 to 1. Next, on this normalized intensity range Rn and Sn, we will perform the power law transformation. So we will use this power law transformation equation considering the normalized input intensity range Rn and normalized output intensity range Sn. We will write down this equation. Sn equals to C into Rn to the power gamma. And in order to understand the power law transformation characteristics for gamma less than 1, let us assume some gamma value which is less than 1. So let us assume gamma equals to 0.2. So in order to explore the transformation curve of power law transformation for gamma equals to 0.2, in this equation of Sn, we will substitute the gamma value, that is 0.2. The equation of Sn, it becomes Sn equals to C Rn to the power 0.2. Now in this equation of Sn, we have to determine the value of C, and for the same we will apply the boundary condition. When Rn equals to 1, Sn equals to 1. So in this equation, in place of Sn, I will substitute the value 1. In place of Rn, I will substitute the value 1, and we will determine the value of C. So if you do the substitution, in place of Sn, I will substitute 1 equals to C into, in place of Rn, I will substitute the value 1 to the power 0.2. If I solve this expression, I will get the value C equals to 1. Now substituting C equals to 1 in this equation of Sn, and we will determine the equation between Sn and Rn. So the equation becomes, so the equation of Sn, by substituting C equals to 1, we will get Sn equals to 1 into Rn to the power 0.2. After determining the value of normalized output intensity range Sn, in last step, we have to convert this normalized output intensity range Sn into unnormalized output intensity range S by performing the simple mathematical operation S equals to Sn into 255. Next, we will do the plotting. Similar to the previous, along x-axis, we will vary the input intensity range R. Along y-axis, we will vary the output intensity range S. Next, we will mark the critical point. This is the origin 0. This is L by 4. This is L by 2. This one is 3L by 4. And finally, this is L minus 1. Similarly, along y-axis, this critical point, it is L by 4. This one is L by 2. This one is 3L by 4. And lastly, this one is L minus 1. So for an 8-bit digital input image, N is equals to 8. L is equals to 2 to the power 8. That is equals to 256. So if L is equals to 256, L by 4, it is equals to 64. L by 2, it is equals to 128. 3L by 4, it is equals to 192. And L minus 1, it is equals to 255. Similarly, along y-axis, L by 4, it is 64. L by 2, it is 128. 3L by 4, it is 192. And L minus 1, it is 255. Next, we will draw a simple table. In first column, we will write R. Our critical points are 0, L by 4. For an 8-bit image, L by 4, it is equals to 64. L by 2, it is equals to 128. 3L by 4, it is equals to 192. And L minus 1, it is equals to 255. Next, we will normalize these values and we will determine the value of Rn by performing the simple mathematical operation Rn is equals to R divided by 255. So first we will normalize this intensity value 0. So 0 divided by 255, it is equals to 0. Next we will normalize this intensity value 64 with respect to 255. So it is 64 divided by 255. It is equals to 0.250, and up to 2 decimal place it is approximated to 0.25. Next intensity value, it is 128. We will normalize this intensity value 128. 128 divided by 255. It is equal to 0.501, and up to 2 decimal place this is approximated to 0.50. Next intensity value, it is 192. We will normalize it with respect to its maximum intensity value, that is 255. If you solve this expression, so it is 0.752, and up to 2 decimal place it is approximated to 0.75. Next, we will normalize this intensity value 255 with respect to its maximum intensity value 255. So 255 divided by 255, it is equal to 1. Next, on these normalized intensity values, we will perform the power law transformation. We have obtained the equation of power law transformation, that is Sn equals to 1 into Rn to the power 0.2. So for each value of Rn, we will determine the value of Sn. So one by one, when Rn equals to 0, in order to determine the value of Sn, in place of Rn, we will substitute the value equals to 0. So it is equals to 1 into 0 to the power 0.2. It is equal to 0. Next, when Rn equals to 0.25, we will determine the value of Sn, and for the same, in this equation of Sn, in place of Rn, we will substitute the value 0.25. So 0.25 to the power 0.2. If you solve this expression, it is equals to 0.757. And next we will round off this floating point number up to 2 decimal place. So it is approximated to 0.76. Next, when Rn equals to 0.5, we will determine the value of Sn, and for the same, in this equation of Sn, in place of Rn, we will substitute the value 0.5. 0.50 to the power 0.2. If you solve this expression, you will get the number 0.870. Next, we will round off to its up to 2 decimal place, so it becomes 0.87. Next, when Rn equals to 0.75, we will determine the value of Sn, and for the same, in this equation of Sn, in place of Rn, we will substitute the value 0.75. If you solve this expression, you will get it is 0.944. Now we will round off this number up to 2 decimal place, so it becomes 0.94. And lastly, when Rn equals to 1, we will determine the value of Sn by substituting Rn equals to 1. We will get 1 to the power 0.2. If you solve this, we will get the value of Sn equals to 1. After determining the value of Sn, in last step, we will determine the value of S by performing the simple mathematical operation S equals to Sn into 255. So for each value of Sn, we will determine the value of S. When Sn equals to 0, value of S, it is equals to 0. 0 into 255, it is equals to 0. When Sn equals to 0.76, we will determine the value of S by substituting Sn equals to 0.76 in this equation. So substituting 0.76 in this equation of S, 0.76 multiplied with 255, we will get it is equals to 193.8. Next, we will round off this floating point number to its nearest integer number. So it is equals to 194. Next, for Sn equals to 0.87, we will determine the value of S. And for the same, in this equation of S, in place of Sn, we will substitute the value 0.87. So the equation becomes 0.87 multiplied with 255. We will get it is 221.85. Next, we will round off this floating point number to its nearest integer number. 221.85 its nearest integer number, it is 222. Next, for Sn equals to 0.94, we will determine the value of S. And for the same, in this equation of S, in place of Sn, I will substitute the value 0.94 multiplied with 255. If we solve this, we will get it is 239.7. Next, we will round off this floating point number to its nearest integer number. 239.7, its nearest integer number, it is 240. And lastly, when Sn equals to 1, we will determine the value of S. For the same, in place of Sn, I will substitute the value 1. So 1 into 255, it is equals to 255. Next, we will do the plotting. First point, when r equals to 0, s is also equals to 0. So when r equals to 0, s equals to 0, represent this origin. Next point, when r equals to 64, s equals to 194. When r equals to 64, s equals to 194, very close to this point, tentatively representing this point. When r equals to 128, s equals to 222. When r equals to 128, s equals to 222. Tentatively represent the middle point, tentatively representing this point. Next, when r equals to 192, s equals to 240. When r equals to 192, s equals to 240, very close to this line L minus 1. And lastly, when r equals to 255, s is also equals to 255. So when r equals to 255, S is also equals to 255. Tentatively represent this point. Next, we will connect all these points. So we have obtained the transformation curve of power law transformation. Considering the gamma value, it is equals to 0.2, and the value of this constant C we have obtained, it was 1. Now let us understand this curve. When my input intensity, it varies from 0 to 64. In the input side, my difference is very small, but in the output side, I am getting a very wide output. This is my dark side. So in this power law transformation curve, when gamma is less than 1, in the input side, my difference is very small. It is 64. In the output side, my difference is very large. It is 194. So here I am expanding. Here I am expands the dark pixel values. On the other hand, look at this bright side. Look at this bright side. The input intensity, it varies from 192 to 255. The difference here it is, the difference here it is 63, but in the output side, the difference is very small. So in tabular form also, we can see when R varies from 0 to 64, in the input, when R varies from 0 to 64, here my difference is 64, but in the output side, it varies from 0 to 194. The difference is very large, representing I am expanding the dark pixel. But look at in the bright side, when R varies from 192 to 255, here my difference is 63, but in the output side, it varies from 240 to 255, and here my difference is only 15. So input side R, the difference it is 63, output side the difference is only 15. So here I am compressing the bright pixel values. Since in this power law transformation for gamma less than 1, and here we have considered for gamma equals to 0.2, we have obtained, we are expanding the dark pixel values, we are compressing the bright pixel values, and as a result, we will get bright image output. It means when we perform the power law transformation on any digital input image, considering the gamma value is considering the gamma values less than 1, and here we have taken gamma equals to 0.2, the corresponding value of C that we obtained, it was 1. In the output, we will get a bright image output. In power law transformation, we are discussing the case study when gamma is less than 1. So once again, the general equation of power law transformation, it is S equals to C R to the power gamma, where R is my input intensity level, S is my output intensity level, C and gamma are the constant. And just now we have plotted the transformation curve for gamma. For gamma value, it is equals to 0.2. We have determined the value of the constant C, it is equals to 1. Similar kind of transformation characteristics for gamma equals to 0.2. It is represented by this nonlinear characteristics, and the value of this constant C in our reference book also it is considered to be 1. This is a small project work. I made it in MATLAB in order to demonstrate power law transformation for gamma less than 1. So image A, it is my input image. On this input image A, I would like to perform the power law transformation for gamma less than 1, and for the same, first this input image A, I make it normalized by using this inbuilt function im to double, and as a result I obtain an normalized image ID. On this normalized image ID, I have performed the power law transformation considering the value of the constant C, it is 1, and the value of gamma, it is 0.2, and as a result I obtain a bright image output. This is in the normalized format. In order to make it unnormalized, I have used this inbuilt function im to uint8. This is the MATLAB inbuilt function in order to convert a image into unsigned integer 8-bit format, and as a result finally I obtained a output image out in 8-bit format. You can observe in histogram plot also, since my input image A, it is a 8-bit image, so the histogram of input image A, it varies from the intensity level 0 to 255. Next, when I make this input image A into normalized, the histogram of my normalized image ID, it varies from intensity level 0 to 1. On this normalized image ID, I have performed the power law transformation, and clearly you can see the histogram of out D, it is shifted towards the right direction. The histogram of image out D, it is shifted towards the bright region, and as a result I obtain a bright image output. The histogram of out D, it varies from intensity level 0 to 1, representing out D, it is in the normalized format. So to make it the unsigned integer 8-bit format, I have used the inbuilt function im to uint8, and as a result I obtained an output image which is in the 8-bit format and whose intensity level it varies from 0 to 255. Another thing that we can observe in this characteristics curve, look at the transformation curve for gamma equals to 0.4, for gamma equals to 0.2, for gamma equals to 0.1, and so on. So as the gamma value decreases, the transformation characteristics curve, it is shifted towards up direction, representing we are expanding our dark pixels more and more, and as a result we will obtain a brighter image output. So the conclusion is that, so as the curve shifted in the up direction, our image output, it becomes brighter, brighter and brighter. So in order to understand this, an example it is given in the book. This is the input image, and on this input image power law transformation has been performed for gamma equals to 0.6, gamma equals to 0.4, and gamma equals to 0.3, and clearly you can see as the gamma value reduces from 0.6 to 0.4 to 0.3, our output image becomes brighter, brighter and brighter. So today I am going to stop here. If you have any suggestion, if you have any doubt, you can write it in the comment section or you can write email to me. Till then, happy learning, have a good day and thank you all.